We're continuing our discussion of nuclear chemistry today. Last time we talked about some history, some basic terminology, and the different particles that are involved in nuclear chemistry. Now, before we go too far, I should have showed you this yesterday as well. This is Table O in your in your reference tables, and this has the names of the particles, the notation, and the symbols. And so last time we talked about alpha particles, beta particles, and gamma radiation. And I noticed for some of these particles there are two different ways to write the notation. I circled the notation that your book uses, so you might find Table O handy. Now today we're going to start our discussion with the measuring of radiation. This is found in section 20.6 in your books. I'll pause for a few seconds so you can copy these notes. Okay, so I'm not going to spend too much time here, but when we're measuring radiation, there's three main things that we want to measure. The first is the activity of the radiation source. The second, the absorption of radiation, and the third, the biological effect caused by radiation. And you'll notice that for some of these, we have a couple of different units to use. So for the activity of the radiation source, the first unit is the becquerel. And this is the unit for the activity of a radioactive source equal to 1 disintegration per second. There's also an older unit called the curie that can be used, and it's equal to the number of disintegrations per second in a 1 gram sample of radium. So these are used for the activity of the radiation source. And radiation sources, the instrument we use to detect it is a Geiger counter. Okay, the second is the absorption of radiation, and the units are the gray. This is the SI unit of radiation absorption equal to the transfer of 1 joule of energy to 1 kilogram of living tissue. And there is also an older unit called Röntgen, and this was originally used to express the ionizing effect of gamma and X-rays. Now this unit is used by physicists, but as far as the absorption of the living tissue, the amount of damage it does depends upon the type of radiation, because you know that alpha particles will not do as much damage as, say, gamma rays. So we need another unit, and that is this third one, which measures the biological effect caused by radiation, and that is a sievert. This is the unit that takes into consideration both the dose of radiation and its impact on tissue. So the gray is the dose, and this also takes into account just that some of these forms of radiation are higher energy than others. And this is used to evaluate radiation's effect on man. So this would determine with your exposure what kind of effect this would have on your body. So that's really all I want to say about measuring radiation. I really want to get to nuclear reactions or nuclear equations for today. So this is section 20.7 in your book, and I will show this to you for a few seconds and then move it down. Okay, so nuclear equations. We wrote equations when we were doing chemical reactions, so we also have equations for nuclear reactions. And this is an equation that describes what occurs when nuclei split, fuse, or release radiation. Now, what can happen is, remember the alchemist always wanted to turn lead into gold? Well, with nuclear equations, we do in fact get different elements, and that's called a transmutation. This is the term given for changing the atom of an element into a different element as a result of a nuclear reaction. So this is what the alchemists were trying to do. And this occurs naturally. Now, when we write nuclear equations, the nuclear equations identify the nuclides, which we'll talk about in a minute, that react, and the products of the reaction. So a lot like our chemical equations, we have reactants, we have products. They also show whether gamma rays, alpha particles, beta particles, or other particles leave the nuclei. So let's go back to this idea of a nuclide. This is a unique atom of an element expressed with the isotopic notation. So just a reminder of isotopic notation, it's in this form: X, superscript A, subscript Z, with X being the element symbol. A is the atomic mass, which is the number of protons plus the number of neutrons. And Z, the atomic number, which is equal to the number of protons. So just a reminder, an example of this, if I have silver 106, 106 is the atomic mass, which is the number of protons plus the number of neutrons. 47 is the atomic number, which is the number of protons. So over here I wrote that silver has 47 protons. And if I wanted to find the number of neutrons, I would subtract the atomic number from the atomic mass and get 59 neutrons. So just a little reminder of how to do that. Now a nuclide, we also need to know it's the term is used instead of isotope when discussing the nuclear characteristics of different isotopes. So nuclides are isotopes. It's kind of interchangeable, but when we're talking about nuclear chemistry, we are talking about nuclides. Okay, so there are different types of nuclear reactions we're going to talk about and equations that we can write. So I'm going to pause for a few seconds and let you copy these down. Okay, these are not all the types, but I'm just having you copy one page at a time. So the first type is an alpha decay. This is the emission, oh, I have too many E's here. The emission of an alpha particle, hence alpha decay. And it causes the atomic number to decrease by 2 and the mass by 4, because if you lose an alpha particle, it has a mass of 4, you're losing 4 mass units, you're losing 2 protons because its atomic number is 2. So let's take a look at an example of this. We have uranium-238, and we're going to say that it undergoes an alpha decay. So it's going to lose 4 mass units, so 238 minus 4 is 234. It's going to lose 2 protons, so 92 minus 2 is 90. Now, this is where we would look this up on our periodic table. And when we do that, we find that an atomic number of 90 is down here, and this is right here, thorium. So I would write TH for thorium plus my notation for my alpha particle. Now notice, as far as balancing equations here, we have to make sure that these are balanced, but what we balance here is we have to make sure that the masses add up, that what's on this side equals what's on this side. So 234 plus 4 is 238, and 90 plus 2 is 92. So that's how we balance these equations. Now, uranium again, but a different nuclide. It's uranium-234. We're going to, again, undergo alpha decay. So 234 minus 4 is 230. 92 minus 2 is 90. We have thorium again, plus an alpha particle. And just double checking, 230 plus 4 is 234. 90 plus 2 is 92. So that's alpha decay. Let's move on to beta decay, because that's the next particle we had talked about previously. So beta decay, this is the release of a beta particle. And this causes the atomic number to increase by 1. So an example of this is carbon-14 releases a beta particle. So remember, beta particles have no mass. So the mass stays the same at 14, but they have a -1 charge. So on this side, I have to think, what -1 would equal 6? Well, 7 would. And if I look up an atomic mass, or atomic number of 7 on my periodic table, I have nitrogen. So this is nitrogen plus our beta particle. Is how we figure that out. And just looking, 14 plus 0 is 14. 7 minus 1 is 6. So it's balanced. We are correct. Okay, so aluminum 28. We're going to undergo beta decay. So mass stays the same. I have to think over here, what -1 will equal 13? Well, that would be 14 minus 1 equals 13. And if I look up 14 on my periodic table right here, I have silicon. So silicon plus my beta particle. Okay, so alpha decay and beta decay so far. There's also what's called positron emission and electron capture. And this explains how the number of protons in a nucleus can be reduced by 1. So the first one we're going to talk about is this positron emission. This is when a proton is converted into a neutron and a positron. We did not talk about positrons last time, but a positron has this notation. So we look at it, 0 mass and a positive charge. And it has a positive charge, but the same low mass as an electron. That's why it still has this beta symbol to it, even though it's a positron. So an example of this would be potassium 38. With positron emission becomes argon 38. So the mass is the same. Over here, +1 charge, so 18 plus 1 equals 19 here. So that's an example of positron emission. Give you a few seconds to write this down. Now, electron capture is also a way that they explain a nucleus being reduced by just 1. And electron capture occurs, and I think you can easily visualize this, when the nucleus pulls in one of the closest electrons and combines it with a proton to form a neutron. An X-ray photon is released. So an example of this type of equation is silver 106 pulls in an electron and becomes palladium 106. So 0 plus 106 is 106. 47 minus 1 is 46. And an X-ray photon is released. Now, the mass remains the same because electrons have very little mass. And a proton is converted to a neutron, so it loses, in a sense, a proton and gains a neutron. That's why the mass doesn't change too, because remember, neutrons and protons have about the same mass. And the last type of equation is gamma emission. There's no change in mass number or atomic number because remember, gamma rays have no mass. They are electromagnetic radiation. They're not particles. So an example would be excited technetium releases a gamma ray, and it stays exactly the same. It's still technetium, but it's releasing radiation. Okay? So what you will see on your test is you'll see some problems like this. And these are from page 512, number 2. And page 523, number 21. So go ahead and copy this top part down. I'll give you a few seconds to do that. And then you may even want to turn off the video, try these yourselves, come back and check it, or have me do a few, watch me do a few, then try some on your own. Whatever you want to do here to get the hang of this. Okay. So I have to bring up a different periodic table here because some of these names, I do not use these very often. I'm going to have to look these up, and they're not, a lot of them are not in your reference tables because they're just not used very often. So GD is one that I have to look up, and that is gadolinium. So gadolinium 150 undergoes alpha decay. So whatever I write over here, I have to make sure it adds up to 150. So thinking 146 plus 4 is 150, or yep, 150. And 62 plus 2 equals 64. So I'm going to put a 62 here. When I look up 62 on my periodic table down here, it's samarium. So that's how you do that problem. You just think, and then double check. 146 plus 4 is 150. 62 plus 2 is 64. It's just simple addition and subtraction here. Okay? So I have curium 245 undergoing alpha decay. So I think what plus 4 will equal 245, and that is 241. And what plus 2 will equal 96? Well, that is 94. So I look up 94 on my table here, and it's plutonium. So Pu. Okay, and just double check. 241 plus 4 is 245, 94 plus 2 is 96. Simple addition. Okay, now I want to know what undergoes alpha decay into fermium 255. So this one's even easier. 255 plus 4 is 259. And 100 plus 2 is 102. Well, I look up 102 and I have nobelium. So nobelium 259. Okay, going on. Barium 141 undergoes beta decay. What is produced? So mass number stays the same because it's plus 0. And I have to think, what minus 1 will equal 56? Well, that is 57. Look up 57 on my periodic table here. And I have lanthanum. Lanthanum. That's one I don't use very much, if you can't tell. If I have to pause, it's probably one I have to look up that I don't use very much. but that's okay. Okay, so E, 32 plus 0 is 32. 16 minus 1 is 15. Look up 15, and I have phosphorus. So phosphorus, 32. Okay, moving on. For F, I have plutonium 239, undergoes alpha decay and gives off gamma radiation. Okay, so this I don't really have to worry about because it's 0, so it won't affect anything. I have to think what plus 4 is 239, and that is 235. And what plus 2 is 94, that is 92. And when I look up 92 on my periodic table, I have uranium. For G, okay, I have zeros here, so the mass is unchanged. I have a -1 and a 0, so I want to think what minus 1 will give me 19, and that is 20. And when I look 20 up on my periodic table, I have calcium. And just double check your math. 40 plus 0 is 40. 20 minus 1 is 19. Okay? So I'm going to pause here for a few seconds for you to copy these down. These are also on page 523, number 21. Okay, so these are very similar problems. The only difference in the directions is it wants to know what type of decay this is. So 242, 242, oh, 0 change. 95 to 96. To get 95, I have to subtract 1. A 0 and a -1, that tells me that this is a beta particle. So this is beta decay. And just double check. 242 plus 0 is 242. 96 minus 1 is 95. Okay, so I have francium 220, and this is going to decay to astatine 216. So let's see, 220 minus 216, that gives me 4. 87 minus 85 is 2. Oh, that looks like it is an alpha particle. So this is alpha decay. And just double checking, 216 plus 4 is 220, 85 plus 2 is 87. For C, I'm looking at my reactant here. So 126 plus 0 is 126. 54 minus 1 is 53. When I look this up on my periodic table, it is iodine. Remember, I look up my atomic number. And right here, this is beta decay because a beta particle is released. And the last one, D here. Alpha decay. So 216 plus 4 is 220. 85 plus 2 is 87. If I look up 87 on my periodic table, I have francium. Okay, so these are pretty straightforward. It's just balancing, adding up the masses, making sure they're equal on both sides, adding up the atomic number, making sure it is equal on both sides. And you will see some of these equations on your test, so make sure you understand how to do that.